Good morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In the last lecture, I was discussing about corrosion, and I took up the different types of corrosion, in which I explained the first type, that was the galvanic corrosion. In continuation with the types of corrosion, the second type of corrosion that we find commonly is waterline corrosion. Now, it has been observed that in the case of iron tank, which contains water or stored water, and the portion of the iron tank which is just below the level of the water, it starts undergoing corrosion due to difference in the oxygen concentration. Now, it has been proved experimentally that the areas where the oxygen concentration is low, that areas start behaving as anode, and the areas of the metal where oxygen concentration is high, they start behaving as the cathode. For example, if we see in this waterline corrosion, this is the steel tank which contains water, and water is not completely filled. There is some spaces. Now, this space above water is only air, and this part contains high oxygen concentration, whereas the part below this water line, this tank, here the concentration of oxygen is low or less, and they are the poorly oxygenated parts. And when the oxygen concentration becomes less, then automatically these parts, they start behaving as anode, whereas the part above water where there is high concentration of oxygen, they start behaving as cathode. As a result, a galvanic cell is formed. Therefore, the corrosion starts. And so, the corroding portion is poor in the oxygen and it acts as the anode. If taking the example of iron, the reactions that are going to take place at anode is the Fe is going to give Fe plus 2 and release electrons, that is, it is going to undergo corrosion, and at cathode, since water is present, it is going to break down into H plus and OH minus. And this H plus, by taking the atmospheric oxygen and accepting the electrons released by iron, will convert into water. And finally, the ferrous ions, they are going to accept the hydroxide ions to get converted into ferrous hydroxide and ultimately into ferric hydroxide. The next type is differential aeration corrosion. Now, this differential aeration corrosion, it occurs on those metallic surfaces which are partly dipped inside a solution of an electrolyte and partly they are exposed to air. Now, in this case, you can see that this is a zinc rod which is half dipped inside an electrolyte which is NaCl solution, and half of it is above the electrolyte. So, again the part which is dipped inside the electrolyte has poor concentration of oxygen. As a result, this part of the zinc rod starts behaving as anode, whereas the part which is directly exposed to oxygen starts behaving as the cathode. And here the different reactions that are going to take place. Now, the anodic part, here the oxidation will take place, so they are going to release electrons. So, zinc will form zinc ions and release 2 electrons, and the water which is present in the NaCl solution and the oxygen and electrons, they are going to form the hydroxide ions, and ultimately the zinc ions, they are going to form, or they are going to react with water and oxygen to form zinc hydroxide. So, the corrosion product will be zinc hydroxide is going to be formed. Now, coming to the different factors which influence corrosion. Now, the different factors which are going to influence corrosion, they can be, the factors are broadly classified into two parts. One is the nature of the metal and second is the environmental conditions in which those metals have been exposed. So, first coming to the nature of the metals, and under that nature of the metals, the first is the position of metal in galvanic series. Higher is the metal in the galvanic series, more is its tendency to undergo corrosion or oxidation. Then second is the hydrogen over voltage. Next is the purity of the metal. If you are using pure metal around 6N, 6N is of the order of 99.9999% purity. That metal, since there are very less chances to form the galvanic cell, therefore it will not undergo corrosion over a long period of time. But if your metal is impure, then again we are going to keep two metals side by side in the same mixture, so there is tendency for the metal to undergo corrosion. Next, relative areas of anode and the cathode. Now, if this is the anodic area and this is the cathodic area, if cathode is more, then the requirement for electrons will also be more. It will be greater if the cathode is more, then the requirement for electrons is going to be greater rather than when the area of the cathode is smaller. So, the areas of the anode should be larger and the cathode should be smaller if we want to reduce the corrosion. Then it is the physical state of the metal, whether the metal is present in the molten state or in the solid form. Then we have already discussed, it also depends upon the nature of the oxide film. Then it also depends upon the volatility and solubility of the corrosion products. If the corrosion products are volatile or soluble, then the corrosion will continue unless and until the entire metal is consumed. Next is the effect of environment. Under the environment, first is the temperature. At low temperatures, other than alkali and alkaline earths, other metals do not undergo corrosion. The rate of corrosion is very less, but at elevated temperatures, the rate of corrosion increases. Next is the humidity. If humidity is less, obviously rate of corrosion is going to be less. Then impurity of atmosphere, more impure is the atmosphere, higher is the corrosion rate. Then is the pH value, then the nature of the ions present, which types of ions are going to be present, if they have the affinity towards the gases or the other oxygen or water, then obviously rate of corrosion will increase. Then next, conductance effect, and finally coming to oxygen concentration and oxygen concentration cell. If the concentration of oxygen is getting varied, then the rate of corrosion will be high. Now, coming to protection from corrosion. These are some general points where we can protect our metal from getting corroded. First is the proper designing of an object. It helps in preventing corrosion. Proper designing means simple designing. The lesser are the L, T, U shapes, the cornered shapes, because in these different shapes, these are the corners, and in these corners the concentration of oxygen is less. So, an oxygen concentration cell will develop and hence the corrosion will take place. Then second is the contact of two dissimilar metals. It must be avoided. Then if it is unavoidable, anodic area should be very large in comparison to the cathodic areas. Then next, if there are two different metals which are being used in a structure, then those metals should be such that they occupy nearby positions in the galvanic series. Then you can prevent by putting an insulator between the two different metals so that they resist corrosion. Then next, as far as possible, the metal used in this structure should be extremely pure. Even the small amount of impurity causes corrosion. Next, while using an alloy, different mixtures of metal, it should be completely homogeneous. More heterogeneity, more will be the rate of corrosion. Next, design or fabricate equipment or metal parts in such a manner that they have minimized sharp edges and corners, and also avoid as far as possible the crevices in the joints. Crevices, these are the gaps in the joints in the case of nuts and bolts. So, more are the cracks, more will be the rate of corrosion. Then the modification of the environment, it helps in protection from corrosion, and modification includes, first, it is the de-aeration removes oxygen by adjusting temperature and mechanical aging. The next, deactivation involves addition of chemicals like Na2SO3, NH2, NH2, hydrated NH2, NH2 which absorb oxygen. Next, dehumidification of environment is done by adding alumina or silica gel. These chemicals, they are going to absorb humidity from the metallic surface. So, lesser is the humidity, lesser will be the rate of corrosion, and we can see in the environment also that during rainy season the rate of corrosion increases because there is a lot of moisture in the environment. Then there are certain chemicals also which can be added to the corrosive environment to reduce the rate of corrosion, and such chemicals, they are called corrosion inhibitors. And broadly, if we classify corrosion inhibitors, they are classified into two different categories, anodic and cathodic inhibitors. For example, the phosphate, chromates and tungstates, they protect the anode. Now, these phosphates or chromates, they form sparingly soluble products which get adsorbed on the surface of the metal, and hence they are going to check corrosion. For example, if this is the anodic areas, this is the cathodic area, if we use phosphate chromates, they are going to form insoluble precipitate, and these insoluble precipitates are going to be absorbed over the surface of the anode. So, the exposure of anode to the environment will be reduced. Similarly, the cathode is also protected by using organic amines, mercaptans, thiourea or substituted urea. Again, they are going to form insoluble precipitate and they are going to cover the cathodic areas. So, lesser is the exposure of anode and cathode, lesser will be the rate of corrosion. And these chemicals, they retard reduction reaction taking place at the cathode. And we can use different salts of magnesium, zinc, nickel, and the insoluble hydroxides of these magnesium, zinc and nickel are going to be formed, which are going to get deposited over the metallic surface, and thus they are going to prevent corrosion. Next, another method of protection against corrosion is cathodic protection. Suppose we are talking about a metal M which is undergoing corrosion, and this metal will undergo corrosion by its oxidation and releasing electrons. So, this is the anodic reaction, and suppose this reaction is taking place in acidic conditions, then this reaction is going to be accompanied by a reduction reaction. So, here the H plus ions, they are going to accept the electrons to form or release or evolve hydrogen gas. Now, we can prevent the corrosion of this metal M by forcing this metal to behave like a cathode. That means if we can by any means reverse this reaction, if we can reverse this reaction in the backward direction, that means the metal, they accept the electrons and getting converted back into the metal itself, then this type of method is the cathodic protection. Now, as there is not going to be any anodic area on the metal, so the corrosion will not take place. So, cathodic protection is nothing but the reaction which the metal is undergoing, oxidation, that reaction should be reversed in such a manner that the metallic ions, they accept the electrons and they get converted back into the metal. So, this is the base for the cathodic protection. Now, cathodic protection is done by two ways. The first method is the sacrificial anodic protection. Sacrificial anodic protection, as the name suggests, to connect our metal with wire to such a metal which is more anodic than our metal which we are going to protect. What I said, if we want to protect M, then this metal should be connected through wire to another metal which is more anodic than our metal. So, in comparison to this metal, our own metal is going to be cathodic in nature, and we have studied that the corrosion always takes place at the anode and cathode is always protected. So, here in this case, what we have done here, this is the sacrificial anode, which is the magnesium rod we have taken, and it is connected through insulated wire to an iron pipe. Since magnesium is more anodic than iron, so all the corrosion will get concentrated on this magnesium rod, and our iron will behave as cathode, and the reaction for iron will be that our iron will accept the electrons and will get converted into the metal. So, ferrous ions, they are going to accept the electrons and get converted into the metal. So, here magnesium is more positive than iron, and hence in the electrochemical cell again this magnesium is going to act as the anode and our iron will act as the cathode. So, we are going to sacrifice magnesium for while protecting our iron. So, this is according to the principle of galvanic cell, that it is the anode that undergoes corrosion, and hence corrosion occurs at anode, saving cathode from corrosion. Similarly, it is also the method which is used in the ships that goes out in the sea, and there are large zinc plates which are hung around the ship hull, the front portion of the ship. So, here large plates of zinc, they are hung through wire, so that all the corrosion gets concentrated on the zinc plates and our ship is protected from corrosion. Next, so here the applications of sacrificial anodic protection. Now, this method is used for the protection of underground cables and pipelines from soil corrosion. It is also used for the protection of ships and boats hull from marine corrosion. Sheets of magnesium or zinc, they are hung around the ship hull, and these sheets being anodic to iron, they gets corroded, and when they are completely consumed, they are replaced by new sheets. Then next application, it is also used in the tanks, and the formation of rusty water is prevented by insertion of magnesium sheets into the domestic water boiler or the tanks. Next is the impressed current cathodic protection. Now, in this case, again the metal to be protected is made cathode and it is connected to the negative terminal of the direct current source. And here the other electrode, it can be made up of graphite or platinum or scrap iron, and this source this source will provide the electrons. This source is used for providing the electrons to our iron or the underground iron, which is to be protected. So, here the positive terminal of the source is connected to the other electrode, which is made up of either graphite or platinum or lead or nickel or scrap iron, and the current in the opposite direction is impressed, and this current opposes the galvanic current. So, galvanic current is that iron will give the electrons. So, we are impressing the current from the opposite direction greater than the galvanic current, so that our ions which are formed, they accept the electrons and they get converted back into the iron metal. And this type of protection method, they are used for large buried structures to prevent them from corrosion. So, we are impressing a current which is going to oppose the galvanic current. That means impresses means that it is applied in the opposite direction to the galvanic current, which is the corrosion current, and hence we are going to protect the metal from corrosion. And this anode, it is buried in the backfill such as gypsum to increase the electrical contact between itself and the surrounding soil. So, coming to the applications, this protection method is very useful when electrolyte resistivity and current requirements are high. It is well suited for the large structures and for long term applications. And this method, again I have said, it is used in the case of buried structures like pipelines, like transmission line, towers and tanks. Now, the next type of a method for protection against corrosion is the application of metal coatings. Metal coatings, whichever metal we want to protect, if this is the layer of the metal, then we can apply the coating of another metal over our metal, so that our metal is not directly exposed to the environment. So, these coatings are again of two types, anodic coatings and cathodic coatings. So, coming first to the anodic coating. Now, these anodic coatings, it is done by a metal which is situated prior to the base metal in electrochemical series. So, it is, as the name suggests, our metal which is used for coating, it should be more anodic than the metal which is to be protected. Suppose if I want to protect iron, then I have to coat it with metal which is higher in the electrochemical series. So, I do a coating of zinc over iron, and this method is also known as galvanization. So, here in this process the base metal is immersed in molten coating metal, and the base metal which we are using, it should be very clear. The anodic coatings of iron is done by aluminium and cadmium also, but these coatings, they protect the metal even though if there is some crack in these coatings. What I said, if the coatings are not, if the coatings break down, if there is a gap in between the coating, even then our iron is going to be cathode and our coating will behave as anode. So, our coating will be anode. So, always till the time this coating, anodic coating is present, our corrosion will not take place at the cathode or at the metal. Now, here these anodic coatings also, they protect the underlying base metal sacrificially, and galvanized iron, it is used for buckets, for wires, for roof sheets. Second type of coating is cathodic coatings. Now, here we are going to protect our underlying metal with a coating which is more cathode, a metal which is lower in the electrochemical series. Now, a metal which is lower in the electrochemical series is going to be less reactive. So, cathodic coatings, they protect our base metal by their noble character. So, here cathodic coating of a base metal is done by another metal which occupies a position below it in the electrochemical series, and by this metal is going to be higher corrosion resistant. One example is coating of tin over iron. If this is the layer of iron, then we do the coating with tin. So, our iron is anode, whereas our tin is cathode. So, because of its less reactivity, noble nature, tin is going to protect our metal, that is the iron. But if there is a gap or a break in this tin coating, then already we have prepared a galvanic couple in which the metal which we wanted to protect is more anodic. So, if these coatings, they are discontinued at any point, then the corrosion of iron will take place at a faster rate, because there is a formation of a galvanic cell. So, these type of cathodic coatings, they are successful only when there is no pit or the crack while forming the layer. So, the coating of tin is called tinning, and tin coated iron, it is used for cooking as well as storage purposes. So, this is how the tin coating is protecting, and if there is any exposed part of the iron, then it is going to get affected and corrosion will be concentrate on iron instead of tin, because tin is more cathodic in nature in comparison to iron. Here are the differences between galvanization and tinning. So, galvanization is nothing but a process of covering iron or steel with thin layer of zinc, while in tinning, these steel or iron, they are covered with a thin coating of tin to prevent corrosion. Now, zinc, it protects iron sacrificially, whereas tin, it protects iron due to its noble character. Then, zinc protects iron even when coating of zinc is punctured or there are cracks, but if the coating of pure tin, it gets punctured, intense corrosion of steel occurs. So, since zinc is toxic, galvanized utensils are not used for storing food, but since tin is non-toxic, so such containers can be used for storing food. Thank you.